you can write down a set of vectors at that point. And at every point, you can write down a set of vectors. So it becomes kind of a vector field. Okay? But I will not talk about vector field at this moment. But let's imagine at the background that when we say we are talking about set of points or set of vectors, this is all at one point in the space or space-time. So set of all vectors form a vector space. Set of all vectors form a vector space. Okay? So let us call this as V. Call it V. Similarly, set of all one forms also form a vector space. Set of all one forms also forms vector space. Now we call this a dual space. We put it as utility. Set of all one forms is a dual vector space. A dual space, and V is a vector space. We have talked about this in linear vector spaces when we talk. In quantum mechanics, I am sure all of you know that in quantum mechanics, the Hilbert space consists of all these vectors, kets, set of all ket vectors, and its dual consists of all these states, set of all bra vectors. And you take a vector from dual, take a vector from Hilbert space, you will get a scalar. Correct? That's how the inner product is defined. So one form in quantum mechanics is simply the inner product phi psi, where this phi is in this dual space and psi is in the Hilbert space. So same concept is true. Same concept, this is more familiar concept for people who are teaching quantum mechanics or who are familiar with quantum mechanics. So, but most often it is very difficult to understand the difference between the space and its dual, because in most cases the space and the dual are actually the same vector space. In some cases they may not be same, but they are isomorphic. That means you can actually write a one-to-one mapping from vectors in this space to dual space. You will see, if you want to actually find the difference between vectors and the one forms, you have to study general theory of relativity, where the space-time is curved, so you do not have a flat space-time. And when space-time is curved, you will see that these two vectors are different. One form is different from the vector. But we can also, in last workshop, we talked about some specific vector spaces where, I'm sorry, I'm referring to last workshop. Many of you may not be there, but let me just tell you that if you consider a vector space of all points in an FCC lattice, for example, then its dual space will be a BCC lattice. So dual space is spanned by reciprocal lattice vectors, and direct space is spanned by direct lattice vectors. So there are some examples like this where your dual space is different from the vector space, but there is an isomorphism. That means for every point there is a corresponding point. You can always connect them through a one-to-one mapping. So that is okay. Now the concept which I wanted to bring out of this entire thing is that if you consider, for example, if you consider, so as I told you, I'm going to use a tilde for one form and an arrow for vector. Okay, this is just to get some kind of familiarity with these concepts. Supposing if I take A times P tilde plus B times Q tilde, that means this is one form, this is another one form, so a linear combination of this one form. If I am sending a vector V as an input to this, then what I will get is A P tilde of V plus B Q tilde of V. Essentially, this is nothing but A times P tilde V plus B times Q tilde. On the other hand, if I have something like this, P tilde acting on A times V plus B times U, these two are vectors, then this is A times P tilde of V plus B times P tilde of U, which is equal to A times P tilde V plus B times P tilde U. Now from these two things what you understand is that the linear form is like a linear operator on V, and vector is like a linear operator on the one form. So there is no difference. You'll see that there is a symmetric action. We have a vector space, and vectors, a linear form is like a linear operator acting on the vector to give a scalar, and vector is like a linear operator acting on the linear form, one form to give a scalar. So they are actually like linear operators. So vectors and one forms linear operators okay, maybe I should write it in this fashion. I can define, just like I have defined here, in this way I can also define V of P tilde is equal to this itself I can write it. And I can write it, this P tilde, this fashion. Then this becomes, the final step is same, this becomes A of V of P tilde plus B times U of P. Then it is clear they are linear operators acting on each other to produce scalars. Which means we can say that the vector this essentially means, I want you to understand the isomorphic nature of these two quantities. So vector is a scalar value function of the one form. Similarly, one form is a scalar value function of a vector. So if you have something like a box here, you send in a vector, you get a scalar. This vector is an input and scalar is an output. Then you call this one a one form. On the other hand, if you send in a one form, you get a scalar, then you call this a vector. That's all. So vectors and one forms are, in this sense, they are linear operators acting on each other to produce scalars.
So the way you define the inner product between P tilde and B, does it mean that P tilde is same as a vector?
Yeah. Right now, as I told you, that there is no difference between a vector and a one form in general, as long as we talk about vectors that they are familiar in flat spacetimes, including Lorentz transformations. But only when spacetime is curved, then you will see there is a difference. Okay, I will demonstrate today. I will not go to curved spacetimes, but I will go to flat spacetimes but curvilinear coordinates and then show that there is a difference. But as of now, right now, as you said, that this is also like a vector. P tilde is also like a vector. I am just putting a tilde just to tell you that it is a member of the dual vector space.
And the first statement that you write here, vector is a scalar value function of a one form.
Yeah.
In which step we have shown mathematically?
As I told you that P tilde of V, we write it as P tilde V, which can be written also as V of P. The definition is exactly same. Because of this, it is like a vector is like a linear operator on this. A one form is like a linear operator. This comes because of that, this is true for linear functions, because linear functionals and one forms are same. Is it too abstract? Yeah.
In that dot diagram you have shown that when you are sending a vector,
Yeah.
you are getting a scalar out. So
Yeah. Then that box is called a one form.
So if it is just a simple vector product, a simple scalar product of two vectors, then the other vector can be called as a one form.
Correct. Correct. So what I am saying is at this moment, it may be very difficult for us to understand the difference between one forms and the vectors. So you have to know, believe me that there is a difference. Right now it is difficult to see the difference. But I am trying to develop this language which will become useful. So, like in that's why I wrote that quantum mechanics notation. So all bra vectors are one forms, all ket vectors are vectors. So in that sense, or if you want to write in the matrix language, all column vectors are vectors, all row vectors are one forms. So that is the way to look at it. And in the solid state physics, all direct lattice vectors are vectors, all reciprocal lattice vectors are one forms. So that is another analogy. It's not an analogy, it's exactly true. So all direct lattice vectors are vectors, all reciprocal lattice vectors are one forms. Okay. Now, since we said that this also forms a vector space, we can ask what is the basis of this one form. Okay, so you can see that since I have already defined the basis, so if E alpha is the basis of vector space V, V alpha is the basis of the vector space V. Remember, this is I don't have I require only some four. If you have a space-time, 4 linearly independent vectors. I don't even have to have any orthogonality. So not necessarily orthogonal. Then we can define the basis of V tilde, that is the dual space. The basis of V tilde, the dual space, as E alpha. The alpha for the dual space I am putting in the subscript, superscript, as E alpha, such that the product of that is E alpha into E beta, E alpha into E beta is equal to delta beta alpha. So this is the product. That means, so maybe I should put it in this way. This is a tilde of E alpha is equal to delta beta alpha, which is essentially, this is nothing but, this is an inner product of E alpha, E beta, comma E alpha. This is equal to delta beta alpha. Delta beta alpha is a very special, where this delta beta alpha is equal to 1 if alpha is equal to b. 0 if alpha is not equal to b. So I am going to follow this kind of a prescription to find out a basis for the dual space. Okay? So